Welcome to Everything Distributed. Today, we are going to continue on the discussion for consistency model for distributed storage. And we are going to focus on an even stronger consistency, which is stronger than the strong consistency that we discussed last time. Last time we talked about more on the client-centric view for consistency and ranging from the strong one to eventual one. And for eventual one, we discussed like 4 different eventual consistency. But something is missing. So if you recall the way we define all those like 6 different consistency model, you will recall that actually the way the definition works is always with respect to one read operation particularly. So here's a reminder. For example, we have like some write operation and then say another write operations. Then the way we define those consistency model is I say we have another read operations. Then we want to focus on this read and define what is a correct value or correct version of data that this read operation should return. But like something is actually missing because that in many other different kind of application, we might need to argue that the relationship between two different consistency model, two different read operation, in this case, R and R prime. And if you remember, like sometime before when I introduced the concept for distributed storage, and one of the ultimate goal that we want to have is that even though we have multiple machines and those machines may crashes and then they are operating on top of asynchronous systems, asynchronous network, we still want the whole system to behave as a one single entity. And today, we are going to introduce some consistency model that try to model this one entity notion. Okay. And then again, as a simplification, we discussed that this shared key value pair or the register idea. So we have a single key and then the value V. And now for all the discussion, we fix a particular key K. So the way we write it is that when we write WV, meaning that we are issuing a write operation that's going to write or update the value V to the particular key K. And since we already fixed key K, I'm going to ignore all the K's in the notation for brevity. And then when I say R, is that I read the key and then it will return some value K, V, okay? And then here I want to warn you that it's very often that I find students when they study consistency model, when they focus on the specification, that they will sometimes get lost and then think about like how could this be possible, and then how do I achieve this? But like for now, actually don't abstract away from the implementation. Just focus on understanding the correctness condition. For example, like if you drive a car or you're going to buy a car right now, you just look at the specification and then you don't really care about like how the car is operating. And right now, just focus on the condition, okay? Otherwise, it's very easy to get lost. And the way we model this like one entity thing, in other words, we want to provide an illusion that you are only using a single machine. And then the key way of you defining such notion in distributed computing is the way called total ordering. And more precisely, we have concurrent operations because we have many clients, many servers, and then they all operating at the same time. And for all those operations inside a given execution, we want to map those operations to a single threaded machines with atomic operations. So there are many key terms. One of them is that single threaded machine. So that's how we capture one entity thing. You can only do one thing at a time. And then the other is this atomic operation. So by atomic operation, if you remember something from computer organization, it's basically that your operation cannot be break up. So you have to complete one operation until you can move on to the next one, okay? So here's an example. Suppose we have 3 clients, they issue like one operation on each of them, say A, B, C. Then here I have some red line, which is the artificial real-time line for the single-threaded machines that we are going to do the mapping, okay? And then if you do this, one simple idea is that you can say, okay, I map this here, and then map B here, and then map C here. So you will say my final ordering is just A and B and C. And then here, for this A, B, C, that's the ordering that we are creating that should make sense for all the 3 clients here, okay? But here just one mapping, because you can say that, no, actually I don't want, you know what, I don't want to do this. I actually want to map C here and then B to here. That's also okay. That's also allowed by the notion for total ordering. So right now, at this point, the way we define total ordering is that we don't really care about what the operation is. We are just have some permutations of our operation. So here we have 3 operations, so you can have 6 possible total order, 6 possible ordering, or 6 possible permutation. For example, ABC, ACB, BCA, BAC, so on and so forth. Okay, so that's the total ordering. Then the next thing is that, okay, now I kind of know what total ordering is, then why should we care? So the first thing, remember here, is a single threaded machine, because that's actually matching our mental model. Like for example, if you have a single CPU, you have a very old laptop, then you can only do one thing at a time and everything is atomic operation. That's the most basic computation model that we know and we are familiar with. So it's very easy to reason with. You don't really need to care about all the possible concurrent operations, okay? And then the other very important notion is that this mapping. So that because even though in reality, tons of operation can occur at the same time. But because you do this mapping on a single machine, so effectively you are asking these questions. Is the given execution that's possibly occur on some single machine? Okay. So here, the given execution is that you have this concurrent operation. But it's possible under some kind of different transformation, some kind of different mapping, that is actually this kind of execution could possibly be observed on a single machine. And then this single machine maps to the idea for this single threaded machines with atomic operation. Sorry, so this is the idea for using total ordering. And then the 2 consistency models that we are going to discuss about today all rely on this notion for total ordering. Okay. So let me clear up the drawing. Then the first one, the notion is called sequential consistency, was introduced by Leslie Lamport back in 1979 in his seminal paper that defines several ideas for how to formalize the correctness condition for multiple process or for this kind of concurrent data structures. The name is called sequential consistency. And the idea is that we have a total ordering. And then the formal way to say that is that for all the operations that's inside the system, even though they are concurrent, We want to do a mapping into an ordering or called a sequence of all the write and read operations inside your inside your execution. Then here, now we actually need to care about the what each operation is. Because if you just do arbitrary ordering, that doesn't really make sense. And here's an example. So suppose that you first just do the mapping from here, and then you do, okay, I'm going to apply R2, and then here I'm going to apply R1. But like if you really try to think about what that each operation is doing, actually this sequence, this ordering doesn't really make sense. Because on a single machine, if you are going to write value 1 into the key, into a register. But the next thing you are going to return, you do a read operation. Why would you return a 0? Where 0 is the, say, initial value. So this R2 shouldn't be here. This R2 instead should map to something earlier. Okay, and then later on, R1, when you do this read, you will going to return 1 because at this read operation, we'll see the effect of this write operation. So formally, how do we quantify this idea? So remember what we are doing? The goal is that we don't want arbitrary ordering. We don't want arbitrary sequence. We want the sequence that can explain the execution. So here, R2 cannot be here because R2 actually returns 0. So effectively, if you want this to be running on a single machines, then R2 has to be the first operation. Okay. And then, so the way we quantify this is called a legal sequence. So if R2 actually occurs here, is like placed here in the ordering, then that's not a legal sequence because this R2 does not see the effect of the immediate write operation. Okay. So how do we define the legal sequence? Legal sequence is defined to be if operation 2 actually return the value that's written by OP1, then operation 1 should appear before OP2 in your sequence, and there's no other write operation between OP1 and OP2. Okay, and that's why we have listing the R2 should occurs before W1. Okay, otherwise it does not satisfy the notion for legal sequence. Okay, so that's the first idea for sequential consistency. You have a total ordering, but it cannot be arbitrary thing. It has to be legal. Okay, then the next thing is that we not just arbitrary legal sequence, we also want it to satisfy the threshold ordering. So what is threshold ordering? If you consider this thing again, we have W1, and then we have W2, and then we have R1. Okay? And then if you do this kind of mapping, again, we run in the same problem as before. This is not a legal sequence because this return thing actually see the effect of this W1. So this two thing has to be side by side. Okay. Now then you are facing an issue, say that where should I place W2 in the ordering that I'm constructing? Then if you say, okay, W2 has to come here, and then I don't place 2 here. So is this a legal sequence? You think about it. So first I have W1, then I have R1, then I'm going to write W2. So that's perfect because R1 sees the effect of this W1. And then W2 just write some value. I never read again, so that's good. But this violates the notion of thread ordering. Why is that? Because at this total ordering, R1 occurs before W2. But from the perspective of this client, this is not actually something happens, right? Because this client actually does W2, and then I do a read operation. But I do an ordering that's kind of should be used to explain all the possible behavior, actually contradicting with this second client. And that's the notion for thread ordering that we want to eliminate these cases, okay? So the way we define thread ordering is that the sequence that you are defining for this red line should actually follow the ordering for each client. So do you see the way we can adjust our ordering so that we can construct such a sequence? Think about it. Let me draw it. So the first thing you know is that in order to be legal sequence, W1 has to occur before R1, and then W2 cannot be in the middle. Okay. Then now last time we also talked about W2 cannot be at the end because it violates the thread ordering. Then what do? Yes, you can actually place W2 here. And then that's your notion, that's your illusion that on a single machine, actually this is something that could have happened. Meaning that W2 is I apply first, and then the machine apply W1. So that's why R1 will return 1, because it sees the effect of the most recent write operation. Okay, so that actually defines the sequential consistency. So let me repeat again. There are three things. First is a total ordering. And then the second is that it's not arbitrary ordering. It has to be a legal sequence. And then final thing is the thread ordering, meaning that the total ordering or the sequence that you are constructing has to follow the order for each client or each thread that you, if you want to think about that way. Okay. Now let's go over some examples. No, sorry, before we go over some example, at this step you might got very confused, say that why should we care about consistency? Okay, I know that there's a way to construct the total ordering, but why? And then the idea is that data storage, you can provide like any kind of consistency. But in order to develop applications, especially that many applications nowadays actually use database to do certain coordination. So for example, if like Facebook, if I post something and then I unfriend you, then, oh sorry, if I unfriend you, then I post something, then I want this ordering thing to be observed, right? Otherwise, when I do certain operations, then it doesn't really, as a user, I don't really expect it to, to have an arbitrary ordering. And then if you want to get to the detail, actually that you want to do all the possible coordination, is very complicated. And that's why that prior researcher, they are really smart. They try to say that, okay, I actually don't know how to argue for multiple clients and how do they interact with each other. I do a mapping. Then everything can be on a single machines. Then that's how I can I can reason with my storage, and I can develop my application on top of storage. So the consistent model is a specification and guarantee for the underlying thing that tells you how you should expect your data should be. Okay. And then how do you know that you already understand it? Is that I give you some arbitrary execution. You need to tell me that does it satisfy, sorry, linearizability is something I'm going to talk about next. But I just said for arbitrary consistency model, you should be able to argue that does this execution satisfy a certain consistency model. And then the next one is that if I give you partial execution and then I tell you that, okay, this execution actually satisfies certain consistency, then you should be able to identify what kind of values that are allowed to return so that the consistency model is still satisfied. Of course, if you are designing about the system, designing the data storage system, or that if there are something that you can tune your consistency model, then you will want to have some idea on how do I implement, how do I achieve certain kind of consistency, and then what is the trade-off, and that's something we are going to talk about not today, but later. Okay? So now let's look at some example like for sequential consistency. Now let me give you this execution. Then you think about it and then tell me that whether this execution satisfies sequential consistency or not. Okay. So remember we have three things. We have total ordering, so everything should be on this real line. And then the second thing is that it should be a legal sequence. The third thing is that the thread ordering. So now let's actually start with the thread ordering. So like what you see is that, okay, W1 has to be before W2 to respect the client one's ordering. And then the next one, you're going to find a place for R1. And because R1 actually returns 2. So you just say, okay, in order for this sequence to be legal, R1 has to be here, because R1 will see the effect of this W2. Okay. Then because and again, I'm going to apply this thread ordering. I say, okay, R2 has to be placed after R1. Then you are going to see that, okay, it's actually not possible for R2 to return 1 because W1, the value 1 is written here. And now at this step, you say, okay, this execution actually does not satisfy sequential consistency. Okay, now let's look at the other example. Now remember for the previous one, because we apply this thing again and again, and then the final step, we say that R2 has to be placed at the very end. But now, what if the R2 actually is not issued by the client 2, it's instead is issued by client 3? Then does this execution satisfy sequential consistency? And the answer is, let's find out. So again, we do this W1, W2, 2, and then we say R1, in order it to be legal, it has to be here. So far, so good. And last time we say R2 has to be the end because the thread ordering for client 2. But since now R2 is at some other client, so you can actually move the place for R2 to be here. Okay, so R2 is here because it's going to return the effect of this W1, and then so that is legal. And since R1 and R2, these two things, they don't have any relationship. R2 can occur before R1, that's okay. It still satisfies this thread ordering. So this is the final execution, and final ordering that we are constructing. And this, because of this ordering, or because of this sequence, this execution actually satisfies sequential consistency. Okay. So you say, okay, then what's more that we can define? This already seems very powerful. We have total ordering. Every client's happy because the total ordering explain their behavior. Now the next one, I'm going to introduce the idea or discuss the idea in this seminal paper by Halahi and Wynn back in 1990. It's called Linearizability. And then this correctness condition actually is defined very generally. It can for like any concurrent objects. So just to remind you what sequential consistency, we have legal sequence, and then we want to have a thread ordering. And then for linearizability, actually there's only one change. If you state the definition this way, which is a real-time ordering. So now consider this execution, and then let me explain to you like why real-time ordering actually makes sense. And here I want to remind you that last time we talked about strong consistency. It's kind of like, okay, if like this thing already completes and any future reoperation should see the effect of this write operation. But like for the sequential consistency, actually it's not the case, because for this one, right, as we've seen before, actually this satisfies sequential consistency, because that, okay, I can have W1 here, and then I can have R2 here, and then I have R1 before. Oh, sorry, here's a typo. This R1 should return 0. Okay. But then this does not satisfy strong consistency, because a W1 has already completed. But like this read does not see the effect of this W1. So that's something not very desirable. And then in many of the application, if you say you are a client, you complete your write, say that, okay, I've already completed my photo upload into Facebook, and then I expect that all of my friends to see that photo because it's a very beautiful photo, right? But like if you do this sequential consistency, actually there's no such guarantee. So that's why we want to have real-time ordering, so that we can make this execution not possible. Okay. So now let's see that what is real-time ordering. So the real-time ordering is that if operation 1 completes before operation 2 starts, then operation 1 has to appear before operation 2 in the sequence sigma. So usually in this kind of notion, in this kind of illustration, what do we mean by complete? It completes at this point, and then this R1 starts at this point. Usually we call this as an invocation event, and then this is a response event. Okay. So in this case, we now know that if we want to do the ordering, W1 has to be placed before R1, and R1 has to be placed before R2. Okay. And sorry, this is 0, which is a typo. So then in this case, you know that actually this does not satisfy linearizability, because R1 should not return 0 at this point. Okay. And then that's the power of this real-time ordering, and it is different from the thread ordering that we saw before. Now let's look at next. Now let's compare linearizability and sequential consistency. So look at this very simple execution. So first, the client does a write operation 1, and then the second client write operation 2. Then now, what's the value that can be returned by R? So linearizability is pretty simpler to argue with, because first I do a write, second I do a write, then because this W2 already completes, so this R should return this 2, because that R should see this, and then that's defined by the real-time ordering. But like for sequential consistency, it's different, right? Because that if you do the mapping, then all I need to do, or all the ordering that I need to respect, is that W2 has to occur before R. But like W1, where I should go, it's possible that I place it here, then in this case, what do R return? It will return 2 because this W2. Or this W1 could be here. So for sequential consistency, actually you can also return 1. Okay, so this shows you the difference between the two. Now let's look at next example. Just focus on the neuralizability. So for this R, what is the value that R can return? So remember the real-time ordering. But in this case, what kind of ordering that we need to respect? We need to respect W1 is placed before W2 because this is the place W1 terminates. This is the place that W2 starts. Okay? Then for R, actually it's overlapping with the 2. So R could be here, or could be here, or could be here. So if R is here, it can return 0. If R is here, it sees the effect of this W1, so it can return 1. And if R is here, it sees W2, so you could return 2. Okay? So that's that. Then next, we see a slightly different example. What can R return in this case? Then again, it's very similar to before, but like we have more constraint right now. So again, because of this real-time ordering, I know W1 has to be W2, and then I also know that the R1 returns the value for W1. So because of a legal sequence definition, R1 has to be here. So now you have to find a place for R2. So what do we know about R2? We know that R2, because of this real-time ordering, R2 actually has to be placed after R1. So R2 could be here, or R2 could be here. So if R2 is here, then it sees the effect of this write operation, so it's 1. Then if R2 is here at this place, what should it return? It should return 2. Okay? So that's that. Then I think this is the final example. I just changed one minor thing from 1 to 2. And for this R2, what could it return? So again, we do this W1 and then W2 because of real-time ordering. And then for R1 to return 2, is that even possible? And then the answer is yes, because this is the time R1 terminates, and then this is the time W2 starts. So they are actually overlapping. And then if you remember the definition for real-time ordering, these two can be placed at any order. So in order for the execution to be legal, R1 has to be placed here. Okay? Then now, because of R1 and R2, this is where R1 terminates, and then this is where R2 starts. Where should R2 go? R2 has to go here, right? And then that's why we have this ordering. So R2 has to return 2 because it sees the effect of this W2. Okay? And that's all I want to talk about for linearizability and sequential consistency. Right now, I know that it's still very confusing, so please work on my more examples, and then next time we will talk about other things. For example, they are under a very similar notion, especially for when we're dealing with transaction. We have this notion of serializability, strict serializability, all different kind of isolation level. And even if we focus on only read-write the shared key value pair register, we still have other kind of tons of the different consistency, auto, causal, PRAM, per key consistency, red-blue consistency, tons of them. And then we only talk about one key and we only talk about read-write registers, but actually the notion for consistency can be extended to multiple keys and to other concurrent data structure. And then one very good thing about the linearizability that I haven't discussed is the notion for locality, which I will discuss hopefully later. And then if you are curious about what are some other popular consistency model, we can highly encourage you to read this documentation by Jepsen. And they provide a very nice tool for practical practitioner, for industry to test their data storage system. And then they also provide a very good blog post and tech report to explain what anomaly that they have find out in real world systems. And Peter Bailis, I think he's now a faculty at Stanford. It also discussed two very confusing concepts between linearizability and serializability. If you know something about database, I also encourage you to read that. And then even though we haven't really discussed the difference in implementation for sequential consistency and linearizability, then the final paper, even though if you are not into theory, this paper is very difficult to read, but it tells you a nice and very clean difference between sequential consistency and linearizability. So you might think that because of the real-time ordering, linearizability is much more intuitive, but under some cases, actually linearizability is slower to implement. And then this paper, the final paper, actually provide you some insights on that. And then the final exercise for you to take home exercise is that you might think that, okay, for all the example, it's very easy to find total ordering that explain everything, and then try this one. Think about that and whether you can find a total ordering for this particular execution. Okay, so the takeaway is that we use the idea for total ordering to provide this illusion that the system behaves as one entity. And then we discuss sequential consistency and linearizability and walk through the examples to understand the difference of their definition. Okay, that's all I want to talk about today. Thank you.